So continuing to our previous topic, we have covered the prevention of deadlock. If you remember, there are four factors that cause a deadlock to happen. So there must be a hold and wait, a no preemption, and of course there must be mutual exclusion and also the circular wait. By having a preventive measure to avoid deadlock, we actually try to control those four conditions from happening. And also, previously, we have covered some avoidance method, which is the Banker's algorithm. So what Banker's algorithm is usually doing is it's just balancing between the availability of resources and the request made by the process for those resources that are limited. So for today, we are going to look at how do we actually determine whether a request from a process towards the availability of resources can be deemed as safe or an unsafe state if it actually needs to proceed. So now we are going to look at how to do those calculations. So before we go further, now we look at some of the definition which is usually involved in calculating whether a state is actually safe or an unsafe state to proceed. So if you look at the diagram below, okay, we have the initial state of a process request and actually to be cross-referenced with the resources that is available. Right? So from this diagram, you see there are the claim matrix, the allocation matrix, and the need matrix, followed by the resource vector and the available vector. So from this diagram, okay, P1, P2, P3, and P4 are actually processes. And also R1, R2, and R3 are the resources that is being requested. So we have the claim matrix, we have the allocation matrix, and we have the need matrix. So each of these matrices also have the information of the process, also the resource information. So how do you actually use this table in determining whether a state or the execution of a process is safe or not? Okay, so the question is, can any of these four processes be executed until completion with the resources available and also based on the request that they made to the resources? So how do we do the calculation? What is the claim matrix? What is the allocation matrix? Okay, so from the diagram, basically a claim matrix is what a process wants. So it's basically telling the OS, okay, I have these resources that I want, and these are the number or the quantity of resources that I want in order for me to actually finish doing all my instruction. And then you have the allocation matrix, meaning that what are the resources that is actually already given to the processes. So from there, we need to actually calculate, okay, now if we actually proceed with the execution of these processes, will deadlock actually happen or not? So if you remember previously, deadlock happened when you don't have enough resources to give to the requesting processes. Okay, so in calculation, how do we do that? Okay, so now please follow through the method. Now, this is usually the initial state of any of the determination problem. So usually you will be given the claim matrix, the allocation matrix, and the resource vector. So how do you actually use this information? So if you remember earlier, you have the claim matrix, what the process wants, and then you have the allocation matrix, what is already allocated or given to the process, and then you have the resource vector. So claim matrix is simply means that what does a process want with the resource and how many resources are needed. And then allocation matrix is what is already given to the process. with regard to the resources. And then you have the resource vector, which is the total resource available in the computer or in the system. And then you have the available vector, meaning after the resources are given to the process, how many are actually left in the system. Now, the calculation for the available vector is usually you need to actually do the subtraction, the resource vector minus the allocation matrix. Resource is the total number of resource that is actually inside the system, and then the allocation matrix is what is already given to the process. So if you notice, if you actually add up all these resource number, okay, 1 plus 6 plus 2, you will have 9. And then for resource 2, 1 plus 1 equals 2. And then resource 3, 2 plus 1 plus 2 equals 5. So allocation matrix that means that, okay, for now, 1 has already been given to process 1. For P2, 6 of R1 is already given. 1 of R2 is already given. And then 2 of R3 is already given. While for process 3, 2 unit of R1 is already given. 1 unit of R2 is already given. And 1 unit of R3 is already given. And then for P4, okay, 2 unit of R3 is already given. So when we need to see how many resources is actually left in the system, you need to actually add up all these numbers, and then you need to subtract with the resource vector. Remember, resource vector is the total overall number of resources inside your computer. So of course you want to actually see, previously you have this, when you already given it to the processors, how many is actually left. So 9 minus, this is actually also 9, then you will get 0. And then 3 minus 2, you will get 1. And then 6 minus 5, you will get 1. So this is the number of resources that is currently available now. Okay, are you following? If you are not following, please repeat what I have explained before we proceed to the next slide. Alright, now once you have calculated the available vector, okay, write down that number and put it aside for a while. Now we need to actually calculate the need matrix. Remember previously we have the claim matrix, we have the allocation matrix. So now we need to actually look at the balance for that claim, which is the actual need matrix that we need to calculate, right? So based on our previous diagram, okay, now we need to calculate the claim matrix. So we have this claim matrix, we have the allocation matrix. Claim matrix, what the process wants. Allocation matrix is what is already allocated or given to the process. So the next step here is to actually see the balance of the claim that you need to actually fulfill in order to determine if those balance process is actually safe to proceed or not. Alright, so in order to calculate the need matrix, you need to actually subtract the claim with the allocation matrix. Okay, so here you have 3 minus 1, okay, you will get 2. 2 minus 0, you will get 2. 2 minus 0, you will get 2. So that settles for process 1 needs. Now for process 2. So process 2, 6 minus 6, you will get 0. 1 minus 1, you will get 0. And then 3 minus 2, you will get 1. So for process 2, only 1 unit of R3 is actually needed. Now for process 3, 3 minus 2, you will get 1. 1 minus 1, you will get 0. 4 minus 1, you will get 3. So this is the balance for the need of process 3. And then lastly, you have P4. Now P4, 4 minus 0, you will get 4. 2 minus 0, you will get 2. And then 2 minus 2, you will get 0. So now you need to actually take care or take note of the balance for the needs for process 1, process 2, process 3, and process 4. So now how do you actually use the previous one, the available vector, with this need matrix? Okay, can you actually guess? You have the available vector, meaning the remaining resource available, and then these are the balance for the request of the process. So how are you going to actually use this information to determine whether a process execution is actually safe or unsafe to proceed? Can you guess? Now, remember that you already have this information. Okay, you already have the available vector information, and also you have already calculated the need matrix. So from that information, you know process 1 needs this amount of resources, process 2 needs this amount of resource, process 3 also needs this amount of resource, and process 4 needs this amount of resource. And then you know that currently the number of available resources for R1, R2, and R3 is actually just this much. So you have 0 amount of R1, you have 1 unit of R2, and you have 1 unit of R3. And then these are the requested number of resources for each process. So how do you actually proceed? So from this available vector, so you cross-check, okay, between request from process 1, process 2, process 3, and process 4, which process request can actually you do first. Okay, so if you are an operating system, you will cross-check this is the resource that you have, and these are the process requests. So from this need matrix, you can see that, okay, based on the available resources that you have, okay, currently you can only entertain P2's request, because P2 request, it just needs one more of resource 3. And based on your available vector, you have 1 unit of R2, 1 unit of R3. So of course, based on that logic, okay, so P2 can actually proceed. Okay, so what's next? So now you can actually determine P2 can proceed with the available resources that we have. So next one, what do we do? Now, this is where all those information comes together. Remember, you have the allocation matrix, you have the available vector, you have also the need matrix. So from the previous decision, you determine that, okay, P2 can actually proceed until completion. Now, another condition is that after a process runs into completion, it will need to release all the resources to a system. So how do you determine how much resources that it needs to return? So this is where you use the information inside the allocation matrix. Remember, allocation matrix is how many resources has actually been given to a certain process. Okay, so by the previous decision, alright, P2 is actually run into completion. So after complete, P2 must release what is already been given to it. Okay, so based on the allocation matrix, now you already allocated 6 unit of R1, 1 unit of R2, 2 unit of R3. So once process 2 actually completes, it needs to return this much resources into the resource vector. So by right, previously you have 0, 1, 1 of resources. Now after completion, you take this value, you add up this value into the available vector. So you return 6 unit of R1 into the available vector, you return 1 unit of R2 into the available vector, and you return 2 unit of R3 into the available vector. So now you have a new value for the available vector. So instead of just 0, 1, 1, so after completion, you will have 0, 2, 3 of those resources. So this value is taken from the allocation matrix. So 6 plus 0, you will get 6. 1 plus 1, you will get 2. 1 plus 3, 1 plus 2, you will get 3. So now the new value of the available vector is 6 unit of R1, 2 unit of R2, 3 unit of R3. So now you have this much resources to be given to the leftover process. So do you know how to actually proceed with this information? Okay, if you are actually lost now, please repeat back to the previous slide. Okay, so now you have this number, the 6, 2, and 3. So now you need to decide, after process 2 has already executed, now between P1, P3, and P4, which process will you actually pick to proceed? Now, so based on your previous decision, now you have this much resources have to be given to the process. And if you notice, I've updated the value for the need matrix and also the allocation matrix. Now you see that the need matrix P2 is already 0 out, and also for the allocation matrix P2 is already also 0 out, because okay, once a process finishes, now you actually cross out the finish process. Okay, so no more needs for P2 and no more allocation for P2. Okay, remember the allocation for P2 has already been returned to the available vector. So that's why right now you already have this much resources in your available vector. So after you have many resources, of course, the next decision is easier, because now you have so many resources to be given out to the requesting process. Okay, so based on the next need information, so you have this much request for P1, this much request from P3, and this much request from P4. And based on the available vector of the resources, you can either give it to P1, P3, or P4. Okay, whichever process that you choose, don't worry, it will get the same result, because right now you have a sufficient amount of resources to be given to either P1, P3, and P4. Okay, because right now you already have 6 units of P1, 2 units of R2, 3 units of R3. So you can either give it to P1, P3, and P4. But for the sake of the example, I will choose P1. Okay, so you can try do on your own. You choose P3 or P4. Okay, because the number of resources is already enough for P1, P3, or P4 to proceed. So either way, it still can finish. So how do you do it? Of course, you need to actually choose. Okay, by right, okay, let's say OS is choosing P1. Okay, so once you choose P1, remember, you need to actually assume, okay, P1 will actually execute until it finishes. So after executing, so P1, it has this much allocation in the allocation matrix. So this much allocation needs to be returned to the new available vector. Okay, so now instead of 6 to 3, you have an extra resource for R1 because you have taken or returned back the resources in this allocation matrix. So now you have the new value for the available vector. So the value increases because P1 has already finished. So by right, P1 needs to return whatever resources that have been given to it. So now you have an extra 7 unit of R1, 2 unit of R2, and 3 unit of R3. Okay, so now after P1 finishes, you also need to zero out this. You need to also zero out this value. So the next one that is needed to be chosen is P3 or P4. Okay, can you decide which one will you choose next based on the number of resources available? Alright, so right now you have 7 units of R1, 2 units of R2, 3 units of R3. And then the number of processes still needed to execute is P3 and P4. Okay, just like before, you can choose either P3 or P4 because right now you are actually rich in resources. So for just example purpose, okay, I choose P3. Okay, so by right, P3 will execute until finishes. And then once it's finished, it needs to actually return all these resources to the available vector. So now you have the new value for the available vector. So previously you have 7 units of R1, 2 units of R2, 3 units of R3. Now after P3 finishes, it will return these resources to the available vector. So 7 plus 2, you will get 9. 2 plus 1, you will get 3. 3 plus 1, you will get 4. So this is the new value for your available vector. And lastly, you will need to actually execute P4. So with this much resources available, now you can, the obvious choice now is just P4 because it is the only process that haven't executed yet. So you actually choose P4 and then after P4 execute until completion. So now you have to return the allocated resource to the available vector. So from 9, 3 and 4, so the last value will be 9, 3, 6. Okay, so it will cross out this one and also this much resources will need to return back to the available vector. So this much resources is actually returned back to the available vector. Now, if you have done all the calculation correctly, you will notice that the amount of the available vector is actually the same as the number of resource vector that we have previously encountered during the start of our calculation problem. Okay, so it simply means that all the resources that you have returned, okay, is actually checking out. Okay, you have this much resource from the beginning, and in the end, you will have the same amount of resources that is actually returned back to the system. So this is how the OS determine whether a process that is requesting the use of resources is actually safe to proceed or not. So if you actually correctly calculate and actually in the end you will arrive at the same number of available vector with the number of resource vector, then the process execution is actually deemed as a safe state. So after that, OS can decide, alright, this P1, P2, P3 and P4 is safe to proceed because you have enough resources to give. Alright, so before we go to the following part of our lecture today, okay, if you still are a bit lost, okay, you return back to the very beginning of my explanation earlier. Okay, and then perhaps you can jot down which part that's actually confusing to you, and then proceed to the next part. So the concept in this method, or also known as the banker's algorithm, is that just like a bank, okay, so you cross-reference the request with the availability of the resources in the system. Okay, so in order to determine whether a process can proceed or not, it is to determine whether the execution is actually safe or unsafe. So that is what you have previously viewed in the example, where it's determined whether a process request of resources is actually safe enough to proceed because we have enough resource to give, or unsafe if we don't have enough resources to give to the available process request. Okay, so the mechanism here is that when a process make a request for the resources in the system, first of all, okay, we need to assume that the request will be granted, and then always update the system state accordingly. Okay, also cross check, okay, whether we have enough resource or not during the execution, and then also based on the decision, determine based on the simulation, is the execution of the process actually a safe state or not. If so, or if yes, the decision after the simulation, okay, yes, it will be a safe state, then it will be granted to the requesting process. If not, block the process until it's safe to actually grant the process request. Okay, so just remember you have this set of amount of resources, and then you have this amount of processes that wants to use that resources. So can this process request be granted or not? You do the calculation and then determine is it safe or not. If it's unsafe, okay, you need to actually wait first and actually wait for the availability of resources until you can actually execute based on your process request. So pretty much that is the banker's algorithm. So the advantage of this deadlock avoidance method is that, first of all, it is not necessary to preempt or roll back processes. It means that once a process actually have executed, okay, after you do the calculation for the next step, okay, there no need to actually roll back to the request of the process. So let's say after a while you determine that, okay, P1 is actually unsafe to proceed. Okay, so that decision, after you do the next calculation, you see that, okay, for the next step, P1 is actually unsafe. So what does it mean? P1 needs to actually be blocked to actually prevent deadlock from happening. So you need to actually give the next order of process to the other process that is actually safe until you have those available resources to give to P1. Okay, so process may still hold on to the resources until the end of the execution. Just make sure that that resources is not needed by the other process. Okay, so this method is less restrictive from the previous deadlock prevention, and process only must be blocked if their continuation might result in a deadlock situation. It means that, okay, after the first execution, okay, you can execute P1, but let's say for the second instruction, you can actually do the calculation. Okay, for the next one, we see that P1 will actually cause a deadlock because we don't have enough resources. So currently, P1 needs to be blocked. So the next order of instruction will be given to the next process if you found that the next process is actually safe to proceed. Okay, so this is where deadlock avoidance have its advantages. Okay, because process still can execute, but if it's unsafe, okay, block that process for a while. After you have enough resource, then that block process can actually proceed. Now, for this method to actually work, these four deadlock avoidance restrictions must be followed. First of all, the number of resources that is required by each process that is in consideration must be declared upfront. It means that, okay, let's say P1 needs this much of R1, this much of R2, this much of R3. So it must be declared to the OS so that the OS can decide or do the simulation or determination accordingly. Secondly, the process under consideration must be independent with no synchronization requirement. It means that the result from P1 will not actually be used from P2, or perhaps the result from P2 will not be used by P1. So they are both independent of each other. Because remember that if it's under consideration, P1 might actually need to be blocked for a while, or perhaps P2 they actually be blocked. So if they are actually relying on each other result, it might of course causes deadlock to happen. For the third one, there must be a fixed number of resources to allocate. It means that you must actually have the actual value of resources to actually consider, so that when P1 actually requested this amount of resources, so you can actually cross-check with the number of available resources that you have inside the system. For the fourth one, no process may exit while holding resources. It means that once a process actually finishes, it must release all the held resources so that it can be used by other resources. So these four restrictions must be complied for this deadlock avoidance method to actually work. We have covered the prevention and avoidance method for deadlock control. Now we are going to look at the third method, which is the deadlock detection method. So how is it different from the previous two? So previously we looked at the prevention method and we also look at the avoidance method. So prevention method is very conservative, where you limit access to resources by imposing certain restrictions. While on the other hand, for deadlock detection strategies, it is actually the opposite of the prevention method. In deadlock detection strategies, resources requests are granted whenever possible, but monitoring is being done throughout the given access to those resources. So how is it different? So this is where we are going to look at in the next section. So the main advantage in the deadlock detection algorithm is that you have a frequent check of the status whether a process actually safe to execute or not. So early detection can be made, and the algorithm is simple because you just do the checking and cross-checking throughout the execution of process. But at the same time, this process will consume a considerable amount of CPU time. So instead of just executing processes at one side, the CPU also needs to check the availability of resources with the process request. So instead of just doing or executing other process, now the CPU time is being used to check whether the resource is enough to be given to the current process. Of course, it can be done faster, but it is determined by the availability of the CPU to do this constant checking. So for the example of the deadlock detection algorithm, first we need to actually look at the diagram. So if you notice, the diagram is actually similar to what we have previously looked at in the deadlock avoidance mechanism. So in this case, you have the request matrix, what is requested from each process. And then we have the allocation matrix, what is already allocated to each process. And then we have the resource vector and the allocation vector. Okay, so if you have this information, how do you actually proceed to decide whether there is deadlock or there isn't deadlock in the system? Okay, so what we see here, okay, follow closely. You need to actually make sure that all processes are unmarked from the very beginning. And then mark all process that is not deadlocked, and then also determine, okay, after that is the safe state or unsafe state from the number of available vector or available resources that you have in the system. So how we'll use those information? So first of all, you need to choose one process that is actually not deadlocked or safe to proceed. So in this case, you see that P4 currently there are no allocation for P4. Okay, so for the first part, mark P4 because P4 has no allocated resources currently. And then for the checking value or the value of W, you choose the value of the allocation vector. So now the value of W is 0, 0, 0, 0, 1. So what's next? You cross-check with the request matrix. Which request can you actually fulfill based on the availability of resources here? Okay, so currently you have 1 unit of R5. And then based on the request, okay, you can see that the only process that can actually proceed is P3 because P3 is requesting R5. Okay, for next, of course, just like before, once P3 is actually finishes, you need to return the value here to the allocation vector. So the new value is 0, 0, 0, 1, 0, which is this value plus 0, 0, 0, 1. So you have now 1 unit of R4 and 1 unit of R5. So after that, which process can actually proceed? Is it P2 or is it P1? Of course, based on the allocation vector, P2 cannot proceed because you don't have R3, and P1 also cannot proceed because you don't have R2. Okay, so in here, you can see that you cannot proceed with P2, you cannot proceed with P1. Hence, you terminate the algorithm because it is an unsafe state because you don't have enough resource R1, R2, and R3 to give out to P2 or P1. Alright, so basically that is all for the detection algorithm. Detection is done on the fly during the execution of the process. But basically, the method is almost similar to the avoidance method because instead of just calculating before the execution of process, for the detection method, it is being determined during the execution of process. If the next process cannot proceed, ultimately you cancel the request of the coming process and just continue with other processes. So by right, the deadlock detection method compared with the avoidance method is that the calculation is being done during the execution of the process. It is actually to detect whether currently during the execution cycle if there is a possibility of deadlock or not. Because in this method, you need to have the OS to constantly monitor the execution of process and it will decide whether it needs to intervene if there is a possibility of deadlock. If let's say you don't have enough resource with the amount of requests coming from the process, so then you can decide whether to forcefully terminate the process or perhaps to release the other resources that have been given to the other process. So it needs to have a combination of method in the deadlock management algorithm. Instead of just relying on one method, so deadlock detection is for the detection and you have other types of control to actually help OS manages the condition inside the system to control deadlock from happening. So again, this algorithm will not guarantee to prevent deadlock, but instead it will depend on the order of the request that is granted and also depend on the help of the other algorithm to help manage deadlock in the system. So the purpose of deadlock detection is just that, to determine whether deadlock currently exists or not in the current execution of a process. How to control it? Okay, it depends on how the OS is actually designed to prevent hanging process or deadlock process if it happens. But the detection is there to actually help OS to estimate or perhaps anticipate before a deadlock actually happen, so that it can prepare the counter mechanism to prevent or stop the deadlock should it actually come. So having said that, this is the last part, which is the deadlock recovery mechanism. So you have the prevention, avoidance, and detection of deadlock. So this method can actually work together side by side. So after you determine or detect there is a possibility of deadlock to happen, what's next? So usually you can do your best for your system algorithm. You can have the prevention, avoidance, and detection algorithm to control deadlock from happening. But as luck have it, sometimes it actually happen. So what to do? First and foremost, the most obvious steps is to abort all deadlock processes. Okay, this is the most common strategy. Either you can have the OS to intervene, or you can have the user to actually intervene. For example, by calling the task manager and terminate the deadlock processes. Secondly, back up each deadlock process to some previously defined checkpoint and restart all the process all over again, which is the rollback and restart process. Third, try to successfully abort deadlock processes until deadlock no longer exists. So for example, you have P1, P2, and P3. Those processes are deadlocked. So perhaps you can try to terminate first process 1 and see whether P1, P2 or P3 can continue. If not, try to terminate P2 and then see whether P3 can actually continue. Okay, if all that is being done, then of course you need to do a rollback if deadlock still happens after you do the successive termination. The fourth one, successfully preempt resources or process until deadlock no longer exists. For example, in this case, you release the resources from the deadlock process. So just like the previous example, now you have P1, P2, and P3 that is in deadlock. So perhaps you release the resource that is being held by P1 first and see whether deadlock still happen. If it still happens, try to release the resource that is being held by P2 and go on until you see the process, all of it can actually continue or not. Okay, so you can try all of this method to recover from deadlock from happening. So depending on how good your OS actually handles this mechanism or whether you can have user to intervene, these are the possible methods to recover from a deadlock. The most important here is that you remember deadlock happens because you have processes requesting for resources that they cannot have. So the mechanism to control this event is actually to have control again to the availability of resources available. Okay, the keyword is you have this much process, you have this much resources. Do you have enough resource to give up to these processes or not? That is the main core of the function of the operating system to manage the distribution of resources to the process. If your OS is actually a good OS, of course, deadlock will rarely happen. But of course, we can only wish, but we must also anticipate if it happens, what can our OS do? So basically, that's all for this chapter. So we have covered in our deadlock is the uh, condition that is contributed to the deadlock. So remember again those four conditions, and how does those four conditions relate to how you actually control and try to manage deadlock. So remember the prevention, the detection, and also the avoidance method to control deadlock from happening, and lastly how to recover from a deadlock. Alright, so by that I end today's chapter, and before I end, after this there is a small exercise that you can do to perhaps jot down your memory of what we have learned today. So before we continue, please remember back what we have learned in the prevention, avoidance, and detection, and then proceed to the next slide for the exercise. So this is something that you could try after this. So here you have the diagram of the claim matrix and the allocation matrix, and you have the available vector. So based on what we have learned today, try to determine whether this is a safe state or otherwise. So try and show your calculation in determining whether this is a safe state or not. Okay, so have a good try. Good luck.